to the course on FPGA based signal processing systems. In lecture 57, we will be looking at the continuation of the discrete signal processing network from the generalized network, as I had shown in the previous lecture as well. So, we have the comb filter part and the recursive, and this is non-recursive one. So, we have the cascade connection of non-recursive, and this is recursive part and the comb filter. So, these cascaded connections to get the y of n, and there are coefficients a naught, b naught, a1, b1, a2, b2, and then c1 also. So, considering this generalized network, what are the different DSP networks can be formed? That is what we are learning, and in this process, as the general transfer function is taken from this transfer function, the diagram can also be obtained. H of z, the transfer function, is having the comb filter, and this is the recursive part, and this is the non-recursive part. So, from considering this second order, we can get many DSP networks from this by changing the coefficients from in this transfer function. So, as an another, the eighth network, that is a real oscillator, and we will also discuss the quadrature oscillator, how the oscillators can be framed from this network. Comb filter, as we know, this comb filter, that is also a part of this generalized network, and an IIF filter, this first order equalizer also, and the cascaded integrated integrator comb, which is an interpolation filter, CAC filter, and then complex frequency sampling filter lane, and DC bias removal, which is also essential to have this in DSP. So, these networks we will see one by one. The real oscillator, the oscillators, I think we are designed to have the output sinusoidal one, of course these things. If we fix the in this network, the general network, the coefficients a1, a naught, a1, a2, b naught, b1, b2, c1, and n. So, here the comb filter part is not applicable in the real oscillator, and then we have only the a1. So, we can get a1 is 2 cos theta, okay. So, a naught is 1. So, we get 1 minus here a1 is 2 cos theta z power minus 1, and a2 is minus 1, that is going to be plus 1 here into z power minus 2, okay. So, numerator part b naught 1 and b1 is 0, and this is going to be minus z power minus 1 2 b2 with that. So, we can have this oscillator, this is going to be the real oscillator, which of is okay. So, from this oscillator, what this theta represents here? So, theta is related to the frequency what we want from the oscillator output, okay. So, this is going to be 2 pi f t, whereas 2 pi f is the frequency, t is here nts, we write in the discrete, 2 pi when you sample it, n by fs, so sampling frequency. So, this n is if it is continuously varying, theta n is going to be varying 1, but we fix this theta not with respect to n. So, theta is going to be 2 pi f by fs. So, fix this fs, what is required and what is f required from the oscillator. So, using this calculation, we can get the fix the theta and get the output from this. And one important thing is, this oscillator will have the needs to be started if it is with some coefficient or the initial condition. So, the z minus 1, because oscillator does not take any input, so it generates the real signal. So, in that case, any of this z minus 1 can be given an initial condition, so that this oscillator start to kickstart the oscillator. We need to give initial condition in this, either use an z as z with initial condition, or give an impulse here to kickstart this oscillator anywhere here, or here. In the adder, we can give one impulse to kickstart it. That way also this oscillator can be started. So, from this, the real oscillators, I got this signal, oscillated signal, in which we have fixed this theta to theta is equal to here pi by 4, okay, and we can get the for theta equal to pi by 4, what is the case here? Theta is pi by 4, then 2 pi f by fs equal to pi by 4. Then we have this here, f by fs is going to be 1 by 8. So f is equal to fs by 8. So whatever you fix fs for this simulation, and divided by 8 would be the f what we get from here. So this case it can be varied according to the theta, we will get the oscillated output. So this is only one signal, real signal, we get it through this oscillator. And the frequency response of it, because wherever we are tuning this theta, that there will be a peak response, that oscillation we will get. So this is for theta equal to pi by 4. And the pole 0 diagram of this particular thing, you have this 2 poles over here and the zeros which are placed in this 2 also. So we have this the pole which is corresponding where we are locating the pole depends on that this oscillation would be. Okay. So here as I told you in the other case also, it will be moved from 0 to 0.5. It can be shifted to any frequency according to this. This corresponds to the fs by 2, then our fs into 0.5. Here is this is the last one. So response can be shifted according to the theta what we keep, and the theta is related to f, and what is the frequency needed, and fs also. So from this the transfer function, and you can have the zeros as and 0 and pole locations are shown over here. So the quadrature oscillator, the next one, in the previous case we have got only one signal, which is the sinusoidal signal. We can, in the quadrature oscillator, we can get this sinusoidal as well as cosinusoidal signal in phase and quadrature also. That's why it is called the quadrature oscillator, the oscillator which can give sinusoidal and the cosinusoidal outputs. So in the general network, how do we achieve that here? So here again theta carries the same meaning, that theta is 2 pi f into t, that is equal to 2 pi f by fs when we deal in the discrete domain. So here 2 pi f by fs, fix that. Here we have the coefficients a1 is e power j theta, and you can see a naught which is g of n, like to talk about this g of n, and b naught is 1 and b1 is 0. So b2 is 0, c1 0, and this doesn't exist as in the case of the real oscillator. There is no co-filter part, and this any of the z should be given an initial condition to kickstart the oscillator. And because this is a quadrature one, and if you see the coefficient e power j theta, this is going to be a complex number. Here we have this a1 e minus j theta, theta is taken as pi by 2 in this case. Okay, accordingly equal to 2 pi f by fs. So we have pi, and this will be f by fs relation will be 1 by 4. So f will be fs by 4. So what you fix this fs, the output will be at. But we get that the output, the complex magnitude and phase, so change it to real and imaginary. So one real would give the sinusoidal, and the imaginary would give the cosinusoidal. So this output we can get it over in phase and quadrature component. But we the oscillator poles depends on this pole location, that 2 poles which are on lying on the unit circle. The oscillation would grow if there is a chance of pushing that pole outside the unit circle, so it never stabilizes. So in that case we need to have a correction factor, that is amplitude gain control, we can say AGC. So needs to be at the output. So taking the output real and imaginary and square this 2, and get a function in which for pi by 2 it would be like there is a x1 square plus x2 square. X1 and x2 are the states of the oscillator. If you consider that x1 x2 in the state space, this can be generally written as this oscillators A, B, C, D. That A, B, C, D can be depends on the oscillations required x1k and x2k. This is the state space equation of the quadrature oscillator. So one state would give the sinusoidal, and the other one give the cosinusoidal one. So ABCD can be fixed, and there is a discrete Barkhausen criteria needs to be followed for ABCD fixation in the case of discrete time oscillators. So here this x1 and x2, what we mean is the states of this oscillator which are real and imaginary parts. So x1 is squared and x2 is squared, then 3 by 2 minus this, there is a condition, and that is going and generating or changing the A naught coefficient. Okay. So, this A naught coefficient, which is g of n, this is going to be g of n. So, generally it is taken as 1, but for stabilization it is better to have the then and there sample the x1 and x2, square it. Also this can be written as like 3 by 2 minus x1 square, when it depends on depends on this. For pi by 2, this is the equation which needs to be followed so that it gets stabilized. So, we have feeding, this is g of n obtained from here and going as an A naught to it in this network. So, remaining coefficients same. So, this is updated every instant of time. So, the quadrature oscillator output, you can see here one is in phase and another one is quadrature phase. Here we have given the less number of samples. So, we have this, but we can one is that, another one is here. So, you can see this, it is starting, one is 90-degree phase shift between the two. So, quadrature oscillator can give two outputs in phase and quadrature. We can choose theta and fs in such a way that to get the nice waveform as well. So, as I said, this is x1 and x2 are calculated this way for pi by 2, and pi by 4 it is a slight change in this formula, that would be x1 square and x2 square will be multiplied with some 0.5 value and then feed it back. So, calculations would follow. Then in the quadrature oscillator frequency response, here g of n is fixed for this responses, because in the time domain it needs to, otherwise it would go unstable. So, we have used the amplitude stabilization, amplitude that is here AGC, automatic gain control, over here. Said automatic gain control, and this automatic gain control is avoided in the case of pole 0 diagram plot and frequency response. Just simply taken one just to show the poles, the pole location is shown over here. According to the theta, this pole location would be, and that particular frequency would be as the output we can get here. This is similar to the that oscillator. The quadrature will be 90-degree shifted from this. So, quadrature real oscillator can give only that one signal, and whereas quadrature oscillator we can get the two types of signal getting generated, sine and cos from that. So, the generalized network can be adjusted with the coefficients accordingly to get these oscillations, or use the oscillator, use it as a oscillator. Comb filter case is known to us. Actually, we have seen that in the examples as well. So, only this part exists and the other parts will be 0. So, you have only one here, B1 other things 0, B1, B2 and C1, and n is taken here 64. We would like to show the output of this particular input what we had given. This is x of n, which has 3 of them, and C1 and z power minus n is 64. So, that except b naught other coefficients are 0, except b naught other coefficients here, this is going to be a naught 1, that is for keeping this. So, here we have this h of z equal to 1 minus z power minus n. So, this 2 a naught and b naught, the remaining coefficients are 0, b1, b2, b naught and all these things 0, a2, a1 as well, and only c1 exists and a naught, a1 is 1. So, this comb filter, if you recall that the comb filter has a gain of 2. Okay, so that is why we divide it by 1 by 2, so that get the signal which needs to be extracted here. So, what is the signal we have used to show the performance of this comb filter here? So, we have the x of n, the input signal, this is x of n, and the one is here y of n, the pink one is y of n, and this 1 by 4 sine 2 pi 25 n, that is 25 hertz is shown over here. This is 25 hertz signal, input signal only, plotted separately to match with the extracted signal. And the 1 by 2, this is 1 by 2 is DC over here, you can see the start, and this is going to be the 50 hertz and then 100 hertz. So, fundamental, second harmonic, and we have this interharmonic also the 25 hertz and DC. So, from that we are trying to extract only the 25 hertz from this and eliminating all of them. So, it is successful in doing that. How what is the response of the comb filter would be, you have the response here, frequency response. So, if you consider this as 0, 50 and 100, the zeros are located in this in this fashion. So, we then 0 will be eliminated, 50 will be eliminated, 100 will be eliminated, only 25 will be passed and 75 will be passed here with high magnitude. The magnitude is 2 here, and then that is, this is 100 and then 150 here. Okay, 125 will be passed, and the remaining frequency also, if you have the closer frequencies, that would also be passed with attenuations, small attenuation. The maximum amplitude for this is 25 and 75 and 125 here. So, the response, this is for omega and h of omega of the plot, the frequency response I can show you. So, you can see the 25 getting passed from this, and the remaining with the amplitude, because it has 2 and we have divided by the amplitude by 1 by 2. So, on even 75 it should be divided by 1 by 2. If the signal contains 75, then it would also be passed from this. So, since we have this 4 components here, DC, fundamental, second harmonic and the 25. So, only 25 is extracted from this using this comb filter. It has different applications like this, we can use it. So, the our frequency response, as we have, this is going to be the 0 at, and this is 0.1 we have shown here. This is corresponding to 0.5, which can be shifted. Here this is considered 50 and 100 for us, and then 150 and so on. So, 50 at 25 we can extract this. This is a maximum 0.2, 0.3, 0.4, 0.5, and around here this is because this needs to be multiplied by Fs. So, so we get the 25 at this point, and we can have the 75 also if the scale corresponding Fs is used in the plotting. And the real axis and imaginary axis, we have only the zeros. Okay, so no pole exists in this comb filter, and this is corresponding to DC, fundamental, second and harmonic, and so on. So, we the 25 hertz was in between. So, we get the response as so which can extract this. So, similarly here as well, so which can extract particular frequencies in that case. So, this is plotted for 8 for clarity, and this particular output we had taken it for with the n one cycle, it is 64. N is 64. So, this is about the comb filter, and then move on to this IR filters. So, you had seen the IR filter design and the coefficients in that. So, in that case we do not have this C1 and N also. These two are only IR filter will have these coefficients B0, B1, A0 and A1, A2, B2. So, it depends on the theta p we have used here. So, this is 0.4 pi and 0.5 pi here into 0.9 exponentials 1. So, B0 is 1, RZ is taken as 0.9, and theta is at B1 is going to be, this is theta is at 0.5 pi, and here is 0.4 pi theta p. So, for real signal sequence we can take that as 0 also, that is these theta z and theta p can be 0. So, that this is giving simply 0.9 and 0.9 having this. So, IR filter can be designed for a passing of frequencies. Here because this theta complex exists here, e power j theta, this needs to be made real and imaginary parts. So, the signal which we had taken over here is this DC, fundamental and second harmonic. So, it is not doing the filtering jobs. A little bit of this you can see, blue one is the input x of n, blue one is the x of n, and this is in phase and the quadrature components. So, it is not eliminating any of this one, it is a low, it is behaving as a low pass filter, it is passing all the frequencies. Even here you can have this DC is little bit, I mean DC is not there, 0.5. But the quadrature component does not have, it also has this components. So, it is not filtering nicely, but we can tune it to have this theta p and theta z also are considered this. So, the response of the filter we can if you make it 0, theta p and theta is 0, so we can have, this is the input, and you have this filtered response. One is one component is 0, and the other component we have this as filtered one, slightly filtered from this input. That's what the higher filter does. So whereas this theta z and theta p are considered to be 0 here for real signal, there is no imaginary component in this. It is the black one shows the 0 1, that is imaginary part, and the signal which is taken is same as that previous examples, but the filtering is little bit, the filtering is done, that is it's acting as a, this is also the 0.5 starting from 0.5, this has a DC in it, the output. The response is here according to the values here, there is a pole in the IF filter and have this 0 as well. So the case is this can be shifted where we want the response band of frequencies to be passed. So this is the peak in which that's why we have all the frequencies getting passed, and the this transition region is also this, so it's not a very good filter here. 0.5 this is going to be 0, so Fs can be fixed and this peak can be shifted to where we want which frequency to be passed, and the rest of the frequencies there will be attenuation in this. So that's why it is around here. So the given input which is slightly smoothening the input signal, that's how this IF filter is. So anyway, this we can locate the poles where we want and make it the transition band very straightened actually, or reduce the slope here so that it can be fixed, but it is giving the response, the frequency response of this particular chosen values is this. Okay, so it's a, we can design this IR filter as well by choosing the coefficients according to the specification and so on, what we had learned already in the IR filter design. So the equalizer is the next network which can be also formed from the generalized one. So the equalizer has the coefficients here, A1 and A0. A1 is a R and B0 is minus R. R is a conjugate. If R is complex number then only, but we are dealing with real signals, so it's not, it doesn't matter that it is a complex here. And B0 is going to be minus R and A1 is R here. So 1 minus R z power minus 1 here what we get. Okay, so the response, okay, R is chosen as, we will have the h of z which is equal to 1 here, minus A1 is R z minus 1 and A2 is 0, whereas B0 is minus R plus B1 is 1 z minus 1. Okay, B2 is 0. Okay, so R choosing 0.7, this is for the first order case. C1 and N are 0, it is not, these are all not part of this. Okay, here this is the comb filter part. A2, A1, A0, B0 here, B0 is chosen as directly 0.7, that is minus 0.7. This is 0.7, R is 0.7. In that case, the location of the poles and zeros can be, so the pole location which gives 0.7 and the 0 which is outside that will be this. The response of this is it's going to be all pass filter, but it introduces it just passes all the frequencies over here. This is 0.5 again, we have this 0 this side. So it depends on Fs, it is passing all the frequencies, but but there is a phase shift in that phase shift is introduced according to the frequencies over here. So this phase shift you can see in the time domain signal R 0.7. So the input which we had given here is this, let's say x of n, and the delay or the time phase shift introduced in the output you can see over here. So this signal is having the 0.5 DC and fundamental and second harmonic. So it is not the output, you can see there is a delay in the output which is due to the phase shift introduced by this equalizer. Okay, but it passes the frequency, it doesn't eliminate any of the frequencies here. So it make this equal all the frequencies. So the output response and the pole zero diagram has been shown over here, which is forming one in the transfer function, here we have this r 0.7. So this is 0.7, z 0.7 to z minus 1 equal to minus 1 equal to minus 1. So you get this pole, and then we equate this to 0, get the 0 from that. So that's how the pole 0 diagram look in this way here. Okay. So next comes the CIC interpolation filter. So this cascade integrator comb filter, it's an interpolation filter which is if used in generally the multi-rate signal processing. Here we look at this filter as a low pass filter. Okay. The coefficient here is it is cascade comb integrator comb. Okay, so integrated filter. So in this case there is a comb filter and there is an upsampler and then integrator, that is the cascade connection of them is the CIC, or if you upsample it and then there will be comb and the integrator. These are the three things in the case of CIC we can see. But this interpolation filter which can be, if you think of the interpolation filter, we have discussed that interpolation filters in the DSC conversion, D2A conversion, where after the DSP processing you get the digital signal. That digital signal needs to be used to up to a particular point, that is to have this decoding. After decoder we use the low pass filter. So the interpolation filters are helpful in that, so to hold the sample for a next sample and hold or first order or second order. This is especially used in the case of multi-rate signal processing, where if you upsample a signal and then process it with the part. So the upsampling is in between, if you introduce what is the value to be introduced there. So decided by this interpolation filter. So but here this generalized network which has the coefficients of a0 1 and a1 is 1 here. So h of z it's going to be the filter which has 1 by a0 1 minus z minus 1, and b1 is 0, b0 is 1, and then all other things, b2 is 0. The c1 has 1, so we have this 1 minus z power minus n, that is a comb. So comb filter and the integrator combination is the CIC. So when you have this it will be similar to, if you recall, we have done the moving averager without 1 by n. Okay, so that is the 1 by n into this transfer function gives us the comb filter. So here is one integrator, then we have this same signal, and taking this as like a moving averager, we plotted the outputs, and it is given 1 by 64. Because of this we are trying to extract the DC from it. So CIC, which is having these comb filter under the integrator, gives only the DC which is present over here. You can see it can be used as a low pass filter which extract only DC, or the moving averager, as in the case of moving averager. So this signal when we give, we try to extract only the 0.5 from this as a low pass filter. So the low pass filter which is having only one pole here, so there is a n zeros on the unit circle, and which cancels only the pole is chosen, the integrator pole which is lying at 1 on the unit circle cancels that 0 here. So we have this 1 which is plotted for n equal to 8, whereas in the previous simulation we had taken n 64, and the this frequency response is for 0 to 0.5, and this can be shifted over here. So this is passing only the DC at this point, and rest of them are attenuated, the harmonics. So if you have the signals in between this, that would be passed according to this amplitude. But we look at the signal where what is the exact application of this particular filters. We've taken those examples in these cases CIC. So looking at as a low pass filter. So in multi-rate signal processing, yes, this is it's a good application which has the comb filter and the integrator it doesn't use any multiplier. In that way it is efficient also. The next one is that complex frequency sampling filters. This FSF filters are really useful in certain cases. It's very interesting to have this FSF filters like. So what is the generalized diagram what we have here is that how to use this one. Okay, so we have this comb filter. Yes, we fix this C1 and N is 64 for this. This is a comb filter. That comb filter is and then comb filter, whatever the band of frequencies we want to pass are deciding the pass band. In that accordingly that resonator can be chosen, k1 k equal to 2, k equal to 3. So the resonator, what we mean is this denominator portion. Okay, so the resonator we have the coefficient a1 equal to e power j theta k and b naught is minus 1 k here. So k theta is again carrying the same meaning here, 2 pi k by n, the number of samples per cycle, and k is bin index, k equal to 1, 2, 3 and so on. So this can be fixed accordingly, that a1 is, so suppose one resonator will have h of z here, suppose here this comb filter, yes, definitely it is there, c power c1 is 1 minus n, and suppose we have take k equal to 1 in this case, b naught is minus 1, so minus 1 per k, okay, the k equal to 1 here 1, and this 1 by a naught is 1 minus here a1 is e power j theta k, k is 1 over here, theta is this, z power minus 1 is delay, and a2 is 0. So this is the one resonator. So and one comb here. So this can be written as 1 minus z power minus n, that is one comb by 1 e power j theta k z minus 1. So this comb and cascade of the resonator. So you can have multiple resonators, k equal to 2, k equal to 3 and so on, so that we can fix the band of frequencies. Suppose I want, this is the k in my frequency, this is 1, 2, 3, 4, and h of omega, what I would like to have is, I want to pass k equal to 1, k equal to 2, k equal to 3. So we will have this, and the remaining k's are zeros. So you choose the resonator according to the k which needs to be passed. Okay, here we have chosen this k equal to 1, 2, 3. For k we mean is here 50 hertz, 100 hertz and 150 hertz. And the comb filter is only one comb filter which has multiple, and then multiple resonators can be chosen according to the band of frequencies which needs to be passed. So and this is adding the three of them, and because this is going to be having the complex number, we convert this real and imaginary and have these gains over here, that is for all of them there's going to be h of k. The h of k depends on that 1 by n, it can be multiplied over the real and imaginary. So let's see this resonator combination cascaded with comb filter is the frequency sampling filter. So we have the samples choosing this sample. So according to the, if you have this k1 here, what we try to have is one resonator output, this is going to be a sinc function, another resonator output k equal to 2, another resonator k equal to 3. So if you add all the three, so this gives the red one here. So in this case, so let's see the output of this one. So we have taken the example here, x of n, the input is having DC, you can see the input having DC and 50 hertz and fifth harmonic 250. So this is x of n now, and the filter what we have chosen is k equal to 1 and then 50 and then second harmonic and third harmonic. If the signal has fundamentals second and third, it would pass the band pass. So but the signal has purposely has this DC we have made to avoid the band passing the band. So in the band of pass band we have only the fundamental and the fifth harmonic which is rejected. So it is passing only the fundamental and the DC is also removed from this signal. So you can see the in phase and quadrature component obtained from this frequency sampling filter, complex frequency sampling filter, which is having the resonator, multiple resonators and one comb filter which is common to the resonators. you can see that rejection of the fifth harmonic, and it is passing only the fundamental here. So, what should be the frequency response and the so it this is 0.5. Yeah, here is again I would like to write it everywhere. So this is 0.1. So here is the frequency starts. Okay, here this is the pass band k equal to 1 to 1 2 3. Okay, this is the pass band. Here n is 16 taken for this. So 16 zeros on the comb, and the poles k equal to 1, 2 and 3. So which forms the band pass band here. So which is cancelling this zeros. So give the peak here in this three portions. So which is giving the response as a band pass filter this way. The band of frequencies which can be passed over this. Okay. So it's a good filter to have this combination of k we can choose, and what are the frequencies. That's why it's called this frequency sampling filter, FSF. The complex in nature because of this e power j theta, which is also the coefficient of it. So these are the rejection band, this side and this side. So the next one is the DC bias removal. We take the DC bias removal case. We want to from the signal we would like to remove the DC. So if you record a signal from the sensor and other things, if it is biased, so you want to remove the DC from that signal. So you can use this network to remove it, and A0 A1 is alpha, A2 B0 and B1 is -1. So H of Z here is giving that comb filter is absent. Okay, and you have these 1, okay, A0 is 1 minus A1 is alpha, Z -1, okay, here, and B0 is 1 minus B1 is this plus Z -1. Okay. So in this case, this alpha we have chosen is 0.98 for closer removing the DC. Okay, so this is like a notch filter, but only for removing the DC, and remaining frequencies are passed through this filter. So we have this response for our signal. What is the similar the one which we had x of n, the previous case also, and the output. This is y of n. You can see the removed DC of 0.5 is removed from the input signal. The pink one shows without DC. Okay, so it starts from here, but it is not having the DC here. You can see the height of this, which is removed in this case. So this is the example of the DC bias removal, which has 50 hertz and 100 hertz and DC as well. So these two components are here retained, and only DC is removed from the output signal. So is a frequency response, this is going to be 0 here, 0.5. So it is very steep when you have the alpha closer to 1, this response, it will pass all the other frequencies except DC here. So this is the pole location of this, alpha is pushing this pole inside. Okay, that is 0.9 or 0.7, whatever. This is not here, as this is closer. This is maybe 0.8 over here. 0.98 is very closer to be this along this. If you move closer and closer to unit circle, the rejection of DC would be proper. So the case of it is the slope also will be steep in that case. Okay. So this is the frequency response and the pole zero diagram of the filter. So to now consolidate or summarize the filters what we had learned here, the real oscillator and the quadrature oscillator, which is used, real oscillator for only the one real signal to generate, quadrature oscillator to the getting the quadrature component as well of the oscillator, and G of n is used for automatic gain control, G of n the expression which we have used, and theta can be chosen in such a way that what should be the frequency required from the oscillator. And the comb filter case can be used for choosing the frequencies in the comb and rejecting the frequencies at the zero location. First order IIR, if we adjust this theta and the theta p in this coefficients, we can get the response of IIR which would like to having. And similarly, the equalizer is again all pass filter and passing only the delays, giving the delays to the output. CAC filter is using this as a interpolation filter here, just it was also taken as the moving arranger type, that one. And we have also seen this FSF, frequency sampling filter, having the band of frequencies which can be passed, and how can we use this as a band pass filter by choosing the different k values. And the DC bias removal is also to remove the DC from the generalized network. We have formed this DC bias removal. The signal input which contains DC can be used to remove the DC from this signal using this DC bias removal network. So, the generalized network, DSP network, which we had seen, so the 15 of them can be formed from the one generalized network with different coefficients, and the characteristics of the frequency response and the pole zero diagram and time domain, how it behaves, has been shown in this two past lectures. Thank you.